Hope that we can start now. Can anyone confirm me that everyone is hearing me? Yeah, thank you. I am sharing my screen with you. I am hoping that you can see my screen. Let's begin today's session. At first, let me introduce myself. I am Hasanul Banna Himel, currently studying at Bragg University. Today, we are going to learn about matrix decompositions. It is linear algebra for AI and ML Day-5. This session is supported with Global AI Community, Dev Changemakers, NSDC, and TensorFlow User Group Bangladesh. In today's session, we will be covering QR decomposition and singular value decomposition. some of the some of you asked me why we are learning this kind of maths or why we are learning this. So we are doing it for ML math clubs. So what is ML math clubs? A solid foundation in mathematical knowledge is vital for the development of machine learning. We all know all the machine learning models are trained with various maths or machine learning algorithms are made with mathematical terms. So how this machine learning algorithm works, for this deep understanding we need to learn about mathematical concepts. So now today we're starting our session. Let's start. At first, let's learn about QR decomposition. In the previous 4 days, we learned about the basic of matrix, what is the what types of matrices are there available. We learned about matrix addition, matrix subtraction, matrix multiplication, and more on. And in the last session, we learned about LU decomposition and PLU decomposition. In today's session, this will be our last session on matrix. In today's session, we will learn about QR decomposition and on singular value decomposition or SVD. Now let's learn what is a QR decomposition. A QR decomposition factorizes a matrix into an orthogonal matrix and an upper triangular matrix. We all know what is a upper triangular matrix. An upper triangular matrix is the matrix in a square matrix in this form. Here lives the upper triangular matrix. And in the next slide, we will know about the orthogonal matrix. And more on the QR decomposition, it aids in solving linear least squares problems and is used in various numerical algorithms. Now let's move on to what is an orthogonal matrix. An orthogonal matrix is a square matrix where the rows and columns are orthonormal vectors. In simpler terms, its columns and rows are perpendicular to each other and have a length of 1. Now it is too much boring that what is written on the slide. Now let's learn something from while doing some mathematical problems. Here is a 3 by 3 matrix. Here we have 1 0 2 0 2 0 0 minus 1 1. Now let's go to our notebook so we can do it there. here we can see that our matrix is here. Our 1 0 2 0 2 0 0 minus 1 matrix is given here. Now how can we solve this? This matrix, our orthogonal basis, or this part will be solved according to Gram-Schmidt method. Now how can we solve this? Let's divide these columns into three parts. Let's assume this is let me change the color. Let's assume this is our V1, this column is V2, and this column is V3. Now write down it here. V1 is our 1 0 0. Our V2 will be 0 2 minus 1, and our V3 will be 2 0 and 1. Now let's assume an array of y. Here we have three components: y1, y2, and y3. And moreover, the y1 is equal v1, or the matrix 1 0 0. Finding y1 is easy. When it becomes hard, when you are finding the y2 or y3. To find y2 and y3, we will use as said before, the Gram-Schmidt method. To find y2, we will use the method, and here we are denoting it as v2 minus v2 multiplied with y1 divided by y1 multiplied y1 whole multiplied by y1. Now let's do it on a side, the multiplication terms. Let's multiply our dot multiplication with v2 and y1. After doing the multiplication, we know how to do the matrix multiplication. We will get a value of 0, as we know if we multiply something with 0, we will get finally 0. So here our result will be v2, and our v2 is 0 2 minus 1. Let's wrote it down: 0 2 and minus 1. Here it is our y2, and we got our y1. Now look forward to y3. For y3, we will again use that method, and the part now will be v3 minus v3 multiplied by v1 divided by v1 multiplied v1 and whole multiplied by v1, and again we are subtracting it with v3 multiplied by v2 divided by v2 multiplied by v2 and whole multiplied by v2 with v2. Now let's do our that mathematical terms. Now we will multiply v3 at first, v3 with v2. Our v3 is 2 0 1, and our v2 is 0 2 minus 1. After multiplying, we will get a negative 1. And now for other parts, now let's multiply v2 with v2. After multiplying this, we will get 5. Now this part our this part is done. Now let's look at this part of multiplication. To doing this, we will now multiply our v3 with v1, which will give us the result of 2. And while we do the multiplication of v1 with v1, after the dot multiplication, we will again get a result of 1. Now let's put our all the values in our equation. We will get a matrix 2 0 1 minus 2 multiplied with matrix 1 0 0 minus a matrix -1/5 multiplied with matrix 0 2 and -1. After doing this, we will get the result. After the whole calculation, we will get a matrix of 0 2/5 and 4/5. Now we all got our y1, our y2 and y3. Now let's put it in our array y. Our y will be curly bracket open, our first y1 or 1 0 0 0 2 -1, and finally our 0 2/5 and 4/5. Now this was our orthogonal basis. Now we will do it on the orthonormal basis. We will find the norm of each of these one, our this y1, our this y2 and our this y3. Now we all know from the previous sessions how to find the norm. Now let's find the norm of y1. The y1 norm of y1 will be 1. The norm of y2 will be √5, and the norm of y3 will be 2/√5. Now this every single individuals, we will multiply this every numerical digit with these values, these matrices. Now let's see what will we get. Let's annotate this with y0. After multiplying this with 1, we will get 1 0 0, and this one, after dividing this with, we will get 1/√5, multiplying 0 2 -1, and finally we will get √5/2, and our values will be 0 2/5 and 4/5. These are our final values of y. And now we will get our q, or what is we're looking for at qr decomposition. We will get the q1. The q will be finally matrix 1 0 0. Our after doing this part we will get 0 2 over root over 5, and after doing this we will get negative 1 over root over 5, and after doing this part we will be getting 0. This one will be our 1 over root over 5, and our this part will be 2 over root over 5. This is our q, or our the orthogonal matrix. Now let's find our r. Sorry for that. Our r will be transpose of q multiplied with a, or our this one, our given matrix. We will multiply this with the transpose of our q matrix. So now we write it down. R is equal q transpose a. Now at first let's transpose our q. After transposing we will be get 1 0 0 0 2 over root over 5 minus 1 over root over 5, and in the last row we will be getting 0 1 over root over 5 and 2 over root over 5, and our a is 1 0 2 0 2 0 0 minus 1 1. Now let's write it down. 1 0 2 0 2 0 and 0 minus 1 1. Now our r, after doing the math or after doing the multiplication, we will get our 3 by 3 matrix. That will be 1 0 2 0 root over 5 minus 1 root over 5 0 0 and 2 over root over 5. Now we got our q, we got our r as said earlier, and we all know that the multiplication of q r, or as the fundamental factor of the decomposition, when we will multiply this q or r, or as we see the previously our plu or lu, while we multiply this we will get our main matrix. So we will write it qr. Our q is 1 0 0 0 2 over root over 5 1 over root over 5 0 minus 1 over root over 5 and 2 over root over 5. Now let's write it down. 1 0 0 0 2 over root over 5 1 over root over 5, and in our last row it will be 0 minus 1 over root over 5, and finally it will be 2 over root over 5. As we can see, this is a orthonormal basis, or this is a square matrix which is also invertible, and this part is our q, and our r will be 1 0 2 0 negative, sorry for that, our root over 5 minus 1 over root over 5, and in the last row we will get 0 0 2 over root over 5. Now we can see that we also got a R, or as we said before, we will get an upper triangular matrix. Here we got our Q and we got our R. After we multiply this one, we will get our main matrix, or this matrix. So this is how we can do our QR decomposition. If anyone has any questions, you can raise your hands. I think I am clear from my side and no one has any questions. So now let's move to our next slide, or our next part, where we're going to talk about the most important one, which will be helping in our to learn machine learning, which is called the singular value decomposition. Now let's look at our main, what is the definition. Singular value decomposition, or also called SVD, is a method to break down a matrix into three simpler matrices. We will be dividing this matrix into three parts. We will be get a E, a sigma, and finally a U. It's like breaking down a complex recipe into its basic ingredients. We will do it with a 2 by 3 matrix. Now let's look into our math. As we done earlier, we see how we done the QR decomposition. Now with the help of this matrix, we will be doing the singular value decomposition. Now let's again go to our slide. We're again into our notebook. Yeah, here we have our matrix. Here we have 1 2 3 4 5 6. Now let's name it as A. We will be needing some things to do this, such as we will need a Y, which needs to multiply our A transpose with our matrix A. Now let's transpose our A matrix. Our transpose of A matrix will be 1 2 3 4 5 6, and our Y will be going to 1 2 3 4 5 6. Now let's multiply this with our main vector, our main matrix. It is 1 2 3 4 5 6. After multiplying this, we will get a 3 by 3 matrix, which will, at the first row we will have 17 22 27. In the second row we will get 22 29 and 36, and in the last and final row we will have 27 36 45. This is our 3 by 3 matrix. It will be useful in the more forward. Now we need to find the eigenvalues. To find the eigenvalues, we need to find the determinant. What will be the determinant? To find the eigenvalues, we will need a lambda. To find the lambda, we will be using determinant of A transpose multiplied with A minus lambda and our identity matrix, which will be a 3 by 3 matrix and which will be is equal 0. The singular values are found from the non-zero eigenvalues, which will be found in the forward parts. Now from this matrix, this matrix, we are going to form the subtracing our lambda from the diagonal entities, our this one. Now after putting our lambda, we will get 17 minus lambda 22 27. In the second row we will get 22 29 minus lambda 36, and in the final row we will get 27 36 and lastly 45 minus lambda. Now let's find the determinant of our this one. The determinant will be, now let's write it as let's write it determinant. Our determinant will be lambda multiplied with negative lambda square plus 91 lambda subtracting with 54. And as we get this, our equation or this part equation will be lambda negative lambda square plus 91 lambda minus 54 and is equal to 0. So we all know how the linear algebras, the roots work. After the calculation, the roots will be, we will be getting 3 roots. The roots we will be getting 3 roots. The roots will be lambda 1, which is going to negative 91 plus root over 8065 over 2, and our lambda 2 will be root over 8065 plus 91 over 2, and finally our last or root 3 will be 0. These all are our eigenvalues. Now as we get our eigenvalues, it is time to get the eigenvectors. It will be helpful for me if you can type this in English. What are they for? They will be useful when we will building or when we'll do the modeling the machine learning models. The eigenvalues. The eigenvalues is helpful to get the eigenvectors. We got these roots, right? We all got these roots. These roots now will be helpful to get the eigenvectors. Is it clear now? I am continuing. Now it is time for the eigenvectors. At first we will be doing this for our root 1. To find the eigenvector, we're doing it this for our root 1 or our negative negative 91 plus root over 8065 over 2. While we do this, we will put our values in our this matrix, this matrix. Let me write it down. 17 minus lambda 22 27 22 29 minus lambda 36 27 36 and finally 45 minus lambda. After when we put the values of our lambda or our root, the values after implementing our values, it will be after the cancellation of negative and negative, it will be minus 91 plus root over 8065 over 2, and others will be same in this row. This one will be same, and this one will be minus 91 plus root over 8065 over 2 plus 29, and the rest will be same in this row again, and in the final row it will be 27 36 45 minus 91 minus we did something wrong. Here it will be positive, and here we will get this one. This one will be here, and after doing the calculation, we will, after doing the matrix, we will get a value of single column matrix, which will be our negative 35 plus 8065, which is root over 90, and our second value will be negative 55 plus root over 8065 over 180, and our last value is 1. This is the eigenvector for our root 1. Now let's do it again for our root 2 or our this value, our root over 8065 plus 91 over 2. Now let's do it again for our root 2. We're skipping some parts, I mean these parts and these parts we all can implement the values. Our final value or the null space will be minus 35 plus root over 8065 over 90. Our second value will be 55 plus root over 8065 over 180, and our final value is 1 again. Now we are going to do it for our root 3 or 0. While we do it for root 0, we all can see if we give 17 minus 0, that will be 17. When we'll do the 29 minus 0, it will be 29 again. So for lambda 3, our null space value will be 1, negative 2 and 1. Now we got our eigenvalues and our eigenvectors. Now let's find the square root of the non-zero eigenvalues. I mean the for root 1 and root 2, as it is non-zero and this root 3 is 0. So for the root 1, our sigma 1 will be root 2 again root 91 minus root over 8065 over 2, and for the root 2, or we will be having our sigma 2, it will be going to have our root 2 root over again root 8065 plus 91 over 2. The sigma matrix is a zero matrix, or this matrix is a zero matrix with sigma initial on its diagonal, or our sigma 1 and sigma 2 will be in the diagonal part. Sorry for that. What is a zero matrix? We all know that in a zero matrix all the values will be 0. So in the diagonal part there will be these values. Here we will have our sigma 1 0 0 0, and in the diagonal here we will be having our sigma 2. Now let's find the columns of the matrix V. All are the normalized unit vectors. We all know that this matrix. Let's write down our matrix V. Now let's change our color. Our matrix V will be negative 7 root over 10 plus root over 3226 over root over 17 root over 8065 plus 8065. Our second value will be -7 root over 10 plus root over 3226 over root over 8065 minus 17 root over 8065, and our last value of this row will be root over 6 over 6. And again, now we are doing it for our second row. For the second row, we will be having 55 minus root over 8065, and over there will be root over 170 root over 8065 minus 80650. Our second value will be 55 plus 8065 over root over 80650 minus 170 root over 8065, and our last digit for this row will be minus root over 6 over 3. And now we have came to our last row. Not this one, or this part. Yeah, our last part will be 180 over root over 170 root over 8065 plus 80650. Our second value for this one will be 180 root over 80650 minus 170 over 8065, and our last row will be root over 6 over 6. We got our, just hold a minute. What? Yeah. Sorry for that, my PC was not working. This was over 6 over 3. Yeah, now we will get our UI. What is a UI? Our UI will be 1 by sigma I multiplied with our main matrix, or 1 2 3 4 5 6, and multiplied with vi, or while we do it will be u1 is equal 1 by sigma 1 multiplied the matrix A and multiplied with v1. After we do it for u1 and u2, we will be left with our final values, or our final u will be uh, 4 root over 298405 minus 3259 root over 8065 multiplied with minus 145 root over 1613 plus 1613 root over 5 over 8065 minus 9185, or and this one will be our u, final u. And now we we told before that the singular value decomposition will be multiplication of u, capital sigma, and v. Now after, when we will multiply our u with our sigma and our final v, we will be back again to our the main matrix, or our matrix A, or 1 2 3 4 5. That is from my side. If you have any questions, you can ask me. I am dropping my social links on the chat box. If you want to improve any of my side, you can suggest me that also. Any questions? Thank you for that. So that is from my side. We have successfully completed our matrix part. Now on the next days we will be covering the vector part and the other parts which is related to linear algebra, and which will help you in the future to learn about more and dive into more in the machine learning. And that is from my side. Thank you everyone for attending this session. Take care everyone.